Our presenter is Slawek Winecki, a senior research scientist at Battelle based in Columbus, Ohio. Dr. Winecki has 25 years of experience as a physical and chemical engineer. His expertise includes development of novel sensor systems, scale-up of chemical processes, chemical reaction and reactor modeling, and development of advanced materials. He's authored numerous scientific reports and peer-reviewed publications, including 2 book chapters, 10 issued patents, and several patent pending applications. Today, he's going to be discussing an improved oil recovery sensor. And Dr. Winecki, whenever you're ready.
Okay, well, thank you, Lindsay, for the introduction. Can you hear me? Can you see my slides? Sorry for technical difficulties. I thank you for the opportunity to present today. I will start with an explanation what kind of sensor we would like to develop. Afterwards, I will move on to the technical explanation how it works. I will start with a so-called dielectric measurement. It's a well-known measurement. I will explain how it works and why it's limited for a type of mixtures we would like to analyze. I will describe our approach to how we solve this problem. I have a few slides to show what kind of accuracy we get from this approach. And last slide, I will present our second version of a sensor, which we currently work on at Battelle, and I will explain its capabilities. We can go to the next slide. Just one quick slide about Battelle. We are the world's largest non-for-profit research and development organization. We are the best known from managing numerous national labs in US, and also we have we are headquarters in Columbus, Ohio. I am based in Columbus, Ohio. We have over 1,000 engineers, scientists working on different projects involving different engineering, some security work, some classified work. Battelle was created in 1923 by Gordon Battelle with a mission to conduct research and development for the benefit of humankind. Let's move on to our next slide, the presentation about the sensor. Can we advance the slide? Thank you. So as you are all well aware of offshore oil recovery operations, the task is to collect oil spill and floating on the top of the ocean. And usually the boom is involved, ships or boats. The task is to collect as much oil as possible, as little seawater as possible. So therefore, BESI recognized that what would be useful, it would be to have a sensor which would be connected with perhaps as a part of a hose used for pumping this oil-water mixture. And this sensor should detect in a real time how much oil is in a mixture. Clearly needs to be a device which will measure any oil content from almost no oil up to almost pure oil and everything in between. It should be able to work with seawater, and it should work with different oil types. It should also be not sensitive to degree of dispersion between oil and water. Sometimes we may have emulsions, and the sensor should be able to handle them. And of course, it should be safe, reliable, economical. BESI requested that the sensor should be built as a flow-through pipe with 2 to 4 inches nominal size. And also it should have wired and wireless communication capabilities. We can move to the next slide. This is getting a little bit technical. Let me try to explain why so-called dielectric measurement is not sufficient. In a dielectric measurement, we examine a material, in this case a mixture of seawater and oil, as a capacitor. So if you imagine this pipe going in or out of a slide shown on a, by the way, I think we advanced to the next slide. Can we? Oh yes, this one. Inside of a pipe is a mixture of seawater and oil, and two metal electrodes are applied from outside. And if one looks at the equivalent circuit of this, we can, the cavity filled with water oil mixture acts as a capacitor connected with a resistance. For typical geometry, let's say 4-inch pipe and properties of seawater, the problem is you may expect capacitance differences of the order of 10 picofarads. This is absolutely fine. Electronic circuits can measure picofarads changes. The problem is if the mixture is conductive, if it's mostly water, this resistor connected in series with this capacitance, it's a very low resistivity, approximately 10 ohms would be typical. This is due to high electrical conductivity of seawater. It can be as high as 5 Siemens per meters. If we have the case of a conductive mixture and we have to deal with this capacitor, with this resistor of approximately 10 ohms, the method essentially fails. So the bottom line, the dielectric measurement works well for low conductivity mixtures which tend to be oil in water, so the water droplets suspended in oil. It really doesn't work for high conductivity mixtures where oil droplets are suspended in mixtures. Let's move to the next slide. One of a common implementation of a dielectric sensor is to use a resonance circuit and detect the resonance frequency. It's what we did in a lab. We had these two electrodes attached to the pipe. It was an external capacitor and an inductor. Values were selected to have a resonance in a megahertz range or a multiple megahertz range. And we used a device called a standing wave ratio analyzer. It's a very low cost device which is commonly used to tune radio antennas. This electronic implementation is not really suitable for a commercial unit. It's just very convenient in a lab. Why don't we move to the next slide? This is how we generated mixture of water and oil in a lab at Battelle. We had a vessel constructed using 4-inch PVC pipes. It was really a closed loop. It could be refilled from the top with oil and water at the different ratios. Therefore, we really knew what's the oil content for this mixture. Once a vessel was filled, we introduced mixing. There is at the top in the middle, you can see a little bit of a motor. It's a variable speed motor with a long shaft and a propeller immersed in a center in a pipe of a vessel, the white pipe on the right side. This propeller generated both flows, a kind of recirculation throughout the loop, and also dispersion of oil in water. We adjust the RPM of this mixer to test different mixing effects. Our sensor is shown on the left side. It's this blue-black device. The nominal size was 4 inches diameter, approximately 24 inches long. Electronics was connected with a laptop computer shown, so we could collect all the resonance frequencies and test different algorithms on this laptop. One comment, you notice that this device excludes air from a mixture because our first version of a sensor, this one, requires that we don't have significant amount of air. This was a limitation for our phase 1 device. Let's go to the next slide. This plot shows essentially the failure of a dielectric measurement for mixtures which are conductive. Let's focus on the plot on the left side. We have a resonance frequency for a dielectric sensors as a function of oil content. you can see as long as the oil content is 70% or above, we have a nice kind of a straight line under the angle. This is a region where the dielectric sensor measurement can give you information about oil content. However, if it's less oil, less than 70%, the resonance frequency is essentially constant, changes a little bit with the mixing properties. You cannot use these measurements to measure oil content. Theoretically, this should get better at higher frequency. Therefore, we also tested this concept at above 230 megahertz. The bottom line is really things are not improving. So the new approach is needed to handle high conductivity oil-water mixtures. Why don't we move to the next slide? We decided, well, we were successful using an eddy current measurement. From elementary physics, you know that the eddy current are electrical currents which are generated if a conductive material is exposed to magnetic fields changing in time. So our idea was to use this as a method to measure how much oil is suspended in water. The idea is if you have more and more oil, the conductivity of seawater should be reduced. Therefore, we will have less of an eddy current. Why don't we move to the next slide? So the implementation of eddy current was, again, we built a resonance circuit. It was an inductor. It had the form of a single wire, copper wire going around 4-inch pipe. It was connected with external capacitor. We selected this geometry because it provides a resonance frequency 15-20 megahertz approximately. Secondary coil, again, a single loop going around the pipe, kind of a 1 inch away. It was connected with the SVR analyzer. Let's go to the next slide. This is what you get from this measurement. 5 plots on the right side, they show the peaks of changing width and height. This is a resonance peak which SVR analyzer can detect. And you can see the shape of a peak, and importantly, its height or amplitude is changing with oil. This is shown on a plot on the left side. So the peak height or amplitude measured in decibels is plotted as a function of oil content. You can see there is kind of a nice, a little bit curved, but very monotonic relationship. However, it depends on the salinity. You can see we have a data for 4 weight percent of sodium chloride and 2 weight percent of sodium chloride. So this means that the user will have to enter salinity of water at a given location. In addition, the sensor needs to measure temperature because electrical conductivity changes not only with salinity, but also with temperature. So let's go to the next slide. So these 2 plots show results of both experiments. On the left side, eddy current, on the right side, dielectric. Both were carried out for a mixture of hydrocol 300 and a water containing 4% of sodium chloride. The point is, these measurements are complementary, and it's very easy to develop an algorithm. So the algorithm goes as follows. The dielectric measurement is done continuously. If the frequency is, well, in this case, around 39 megahertz or higher, we use this value of a resonance frequency to measure oil content. It would be 70% or more. If a resonance frequency it happens to be lower than 39, the algorithm knows that it needs to use the eddy current data shown on the left to measure oil content. Let's go to the next slide. This is what you get using this simple concept. So this plot is a correlation plot. Horizontal axis is a true oil fraction. It's based on the amounts of oil and water we introduce into our apparatus. And the vertical axis is it's what we got from our sensor. We tested 4 types of oil, 2 refined oils, hydrocol 300 and colsol. And they differ, they have a different viscosity, and also 2 crudes. We use the hoops and the Pacific Energy. All of this was done for 3 values of salinity, 2, 3, and 4 weight percent. Well, it's not ideal measurement, but we claim it's quite good for particularly for this application. Correlation coefficient is as high as 99%. The average error is 3%. It's kind of an average deviation between these points, experimental points, and the ideal diagonal line shown on this. The maximum error is plus 12%, minus 10% on a kind of absolute value. So there is somewhere this points, 12% above diagonal and 10% below diagonal. Not ideal, however, for we believe for oil recovery application, this can be very useful information. Let's go to the next slide. How about, so the previous slide, it was laboratory data. We went to OMSET to test our sensor. We have a couple of pictures. You see a picture on the right. The OMSET technician is adjusting some connections on top of our sensor. It was mounted vertically, and testing was done in the summer of 2018. We tested 2 hydrocarbons, hydrocol 300 and a diesel fuel. Both were tested with water with 2 salinities, 1.55% and 3.6%. Over 5 days, approximately 60 mixtures were tested. We can go to the next slide. So this is again correlation plot using all OMSET data. And correlation coefficient was slightly lower, 0.96. The average error, 6.1. The maximum error was 21%. There is one kind of a red data point at a 70% true oil fraction. Well, overall, we believe it's still very good accuracy for this application, specifically because there is currently no device able to measure oil fraction in a flow through real time setting. We are from the discussions with Bessie, we understand that the substitution, really what we are competing with here, it's a kind of visual evaluation of a stream. If a stream appears to be viscous and black, it's most likely oil. If a stream is less viscous, lighter in color, it would be a lower amount of oil. We welcome this competition. We believe our device will provide much better information for during oil recovery. Why don't we go to the last slide? Yes. So this is our second version of a sensor. It works slightly differently. It's being developed. We plan in the next 2-3 months to go to OMSET to again test it. And this is really intended to be tested in an industrial setting somewhere, perhaps the Gulf of Mexico, perhaps Alaska. The major improvement in capability that this is a 3-phase sensor. It will account for air in a pipe, and it can measure, really a mixture of oil, water, air. It's designed to operate horizontally, to be connected with hoses on both ends. This sensor will have a wireless and wired communication. For wireless, we use the frequency of, I believe, 915 megahertz, which is effective in a marine environment. It's not trivial, as you know, to have a radio communication close to the sea level. It will operate from -25 Fahrenheit to 120 plus 120 Fahrenheit, so very broad temperature range. The sensor will only take half a watt of power. So actually the tablet, which would be provide output to the user, will take much more power. The sensor by itself will operate for much longer time on a lithium battery. And I have an acknowledgement slide. We can, yes. So this work was sponsored by BESI, phase 1, starting in 2017, ending 2018. It was BESI project 1083. The current project started in October 2019. It will end in midsummer, basically. This is the BESI project 1119. If you like to learn more about this phase 1 sensor, what I described today, we published a journal article. It's published in Journal of Sensors and Actuators, Physical. Title is Improve Oil Recovery, 2019. We have 3 patents. The first patent really covers the phase 1 sensor I described today. 2 additional patents really address and protect the second version of a sensor. This is all what I have.
Thanks, Dr. Winecki. I have a question to start. So sorry if you covered this in the first few slides of your talk, but do you foresee that background noise would be generated from something like suspended sediments or algae in environmental systems?
I think based on how the sensor works, it will kind of look what's the water versus oil content. If you if you have some bioorganism inside of a cavity, the sensor will really evaluate, is it mostly water or is it mostly oil? I don't know what, if you have a fish inside, I don't know if it happens. You may have a few % of water, and the sensor will kind of evaluate where there is some oil in this. And this approach is known to measure fat content in a tissue of animals and people. So the algae, I think algae will be seen mostly as water. I don't think it's much of a fat in an oily substance in the algae. Maybe I'm wrong.
Excellent, thanks. And Jenna, do we have any questions?
Does not appear that we do.
Fantastic.
One just came in.
Got it.
Can this sensor work alongside other sensors?
Yes. Specifically, we are working with BESI to incorporate a flow meter signal. So the software can integrate how much oil is being collected. Sensor by itself cannot really detect the flow. It's not aware of it. It only looks how much oil is inside of a cavity. But we will have a capabilities of an output from a flow meter sensor can be connected with our sensor, and the software will display oil fraction, but also how much oil is collected. This is separate kind of a project. It's not easy to measure flows. We learn of this type to get how many gallons per minute are being collected. But this is kind of, assuming this problem is being solved, our sensor will be able to integrate based on a flow meter and an oil fraction measured.
All right, no further questions.
Okay.
Thanks, Jenna. Thanks, Dr. Winecki.